Yeah, thank you everybody for coming. Uh, Today I'm going to talk about it's this informal report, right? Series we have about the variability of the Brazil current and some regional impacts. This is part of an NSF grant and also related to the XPT project at NOAA. So a little introduction of the western boundary system in the South Atlantic. So this is the South American coast, the Brazilian coast. So I have the a system of currents. First, we have the bifurcation of the South Atlantic equatorial current, and into a northward branch and a southward branch, and the southward branch is called the Brazilian current, which bifurcates at different depths and have contributions depending on the latitude we are from the bifurcation at different intermediate water, and of course the deep western part. It's weaker, much weaker than the Gulf Stream because of the more contribution northward, which enforce the Gulf Stream and weakens the Brazil current. And this western boundary, even though it has a strong eddy variability, as you see here, especially in this region between 20 to 25 south, and its dynamic is associated with the coastal upwelling, especially in Cabo Frio, which you have associated with the meanderings of the Brazil current, as well as other process during summer. And the Brazil across 22 south, we see that from Limerol, a student from Brazil who we collaborated with him in 2016, and the folks from Brazil, we see some comparison with some high resolution reanalysis. We see that a lot of the Brazil current, part of it flows on along the shelf, which is hard, really hard to measure. For example, through Argo and other products. So it's about we're estimating in the models about 30% of this is along the shelf. So is a large contribution with this, especially that is caught in a high resolution. So you need a high resolution model to resolve. And of course, we have all these mesoscale features. They are related to they enhance the coupling between the ocean, and which the ocean managed to force the atmosphere. And here is one example from a high resolution couple model and a low resolution couple model, which I'm going to talk later on. But we see a lot of the contours here is a wind stress curve and the gradients of SST, and you see that a strong coupling between these mesoscale features and the wind, of course, and of course along the boundary where you have stronger currents, and of course the Gullas region, and we have a really strong. This interaction is even stronger, and it's generally not captured in low resolution models. So we need so a lot of these interactions may not be represented in our climate models. And it has an impact in climate. This is interaction. So this is the monsoon, the global monsoon system. And here in the South Atlantic, we have the South Atlantic convergence zone that is typically strong during the summer months in the southern hemisphere. And it's associated with the moisture from the ITCZ and from the Amazon region that flows southward in this low-level jet, and it has interaction here along the boundary when you have this cyclonic circulation. So you have an intensified South Atlantic convergence zone and precipitation in this region. And these events are generally linked to summer floods, especially in Rio and São Paulo, and the region with over 30 million people live in that area. So a lot of people are affected by that. And so the objective here, two main objectives. One is to investigate the variability of the Brazil current in seasonal and terrenal timescales, and the other associated to mechanisms and impact of that variability. And the second part in using a climate model framework. So the outline, a quick outline for these two parts. The first part, we are going to explore the synergy between XBT data and altimetry and extend this time series of the BC, the Brazil current. This will focus especially on 22 South. And the second part is investigate the BC and the Brazil current and their sea interaction in the West and South Atlantic. So how we measure the BC? As I said before, it's really hard to measure with Argo, because Argo, we miss this whole 1,000 meters inshore. So we have along the western boundary, we have three main transects, the AX97 from Rio to Trinidad Island. We have this AX17, I don't know if I can call that, but is a part of the AX18 that flowed 34.5 south, but a few of the transects, they went all the way to Rio. So we have mostly three transects that we can estimate that. And the XBTs, they measure temperature in the top 800 meters of the ocean in a high spatial sample, so we can measure mesoscale. But yeah, this data, we need to add more data to be able to measure like variability of the current and geostrophic currents. So the methodology to estimate the BC in the XBT data, first we need to use salinity, which we are using here. This is a paper in preparation, but we are already using some of the results on that, a new estimate of salinity. And we have reference velocity, generally use Argo at 500 meters, so we can have the absolute geostrophic current. So this is just climatology at the reference level. So this 500 meters is more or less where we have a separation in that region between the upper tropical waters from the intermediate water. And we try to do an extrapolation to the south to go all the way to the western boundary, because some of the transects they end short of that land. So several papers in the past they explored this, basically extrapolating, and I know that people have done that with using climatology, but there's an error associated with that. So we try to explore on that using altimetry as well. And so we need to determine altimetry to compare with the dynamic height anomaly, because altimetry that this mass loading that dynamic height doesn't have, and especially this is especially important when you try to estimate with the synthetic method to use regressions. And these regressions, we assume they are steady in time. So this is an important part. And of course, we are going to extend the altimetry using the time series using altimetry data. So first, I'll go to a few of those points for how to extrapolate to the shelf. So here we have one of the sections here with the dynamic height calculated from temperature and salinity in the XBT in blue, and the sea surface height or sea level height from altimetry. And we see that they are pretty comparable. And we see that altimetry will go all the way to the shore, whereas in this particular section here, it's for around 40 west. So we try to estimate that. So we use the gradients of altimetry. So this is as a reasonably simple method, just to estimate the gradients from altimetry and extrapolate that to XBT. And we see that some of the sections in the AX97, they generally stop around here, and then we extend all the way to the shore. And here is one of the sections that we extended. This section here associated to this, we got to go until 40, and we managed to estimate all the way to the shelf. And so for the system phase height correction, we know if we compare the dynamic height and system phase height estimated from XBT and from altimeter, we see that there is this red line. We see that there's variability, of course, associated with the barotropic modes that we use just climatology. But there's a trend associated with that. And this trend is what I think associated to the mass load of the ocean. And some people estimate that as 60% of the system phase height increase over time is just the mass contribution as opposed to the static contribution. And then if you see, just get one estimate here of the basin around the South Atlantic basin, and you see that the trends are pretty similar for the period of the XBT. So we need to extract this trend to be able to have a steady relationship. And when we do all these procedures, what we have between altimetry and dynamic height, we have a pretty good agreement all the way to the shelf, and including the interlinear variability. And these are the residues at the few locations where this could be related, of course, to the barotropic component and other features not resolved. But the agreement is generally pretty high between the two. So this gives confidence on how to produce a synthetic estimate using altimetry. Yeah, just for another application that I'm not going to talk about here, but a lot of study DayMOC, the same MOC at 34 South, and this has been used also at 34 South, and you have pretty much the same agreement which we have at 22 South, and here's altimetry and dynamic height, and we can extend all the way to the shelf too, so we can measure the Brazil current all the way to the shelf and estimate the transport. So here at 34 South, we have just 26 sections, and the mean transport is about 12.4 is variable, which is in pretty good agreement with the previous estimates. But go back to the 22 South. So what we want to do, we have the altimetry time series along the X97, far between 45 and 30 west, and we want to estimate the transport of the Brazil current. And see, here's just a Hofmöller of the sea level height anomalies, and you see some of the features that we have been reported before. For example, in 2001, we have a really strong São Tomé eddy where we have this meandering of the Brazil current totally detached from the boundary for a few months. So to estimate the transport, some people calculate, use that as 39 west. A few papers like Pereira et al. And other people, especially in Brazil, they do that. But this may not be the best estimate, especially when you have an event like that you can lose completely the Brazil current. So two methods to estimate. One is calculate the transport using the maximum system phase height value and with this gradient when we don't have real velocities, or calculating from the velocity fields, but using the minimum or the maximum transport, minimum because it goes southward. So we are going to apply two methods to estimate the variability of the Brazil current at interannal time scale. One of the methods is just using sea surface height. So we assume the gradient of sea surface height of the surface, and we assume that it spreads through a depth h, and this depth h we are going to regress against observation, and here against the X97 transport. And using this method, we can have a pretty good agreement between the transport estimated just using sea surface height and using the true transects. So, and then we have this h of about 130 meters depth. And another method, I'm not going too much into the detail, but this is a synthetic method that a lot of us use, something similar, which we have the dynamic height anomalies are related to the dynamic height anomaly at the surface. And then when we take this, when we put the mean dynamic height to get the total dynamic height, and then we regress that to sea surface height. So we can go from dynamic height to surface height at depth. So this is a little movie of what we get at 22 South using this method. So we can have daily estimates of the Brazil current. We see that a lot of westward propagation in the region. We see that the Brazil current sometimes populate the shelf with a stronger contribution. And so we are going to use this to calculate the transport of the Brazil current. And so first we calculate the seasonal cycle, and the seasonal cycle using the three methods: the XBT, the synthetic method, and just the sea surface height. So we have the XBT only because of the high variability and the high eddy variability. It's really hard to get a seasonal cycle of the Brazil current. Whereas the two other methods, we can have a pretty reasonable seasonal cycle here with the stronger Brazil current in February, March. Of course, it varies a little bit here, but the curves are pretty similar to each other, and low variability in June, July. And then we estimate the time series, the total time series of the Brazil current since 1993 using this method. And the dots here are the XBT's observation and the two reconstruction methods. And they agree pretty well in between them and with the observations. And we get a mean of 4.2 Sverdrups. And along the shelf, we get around 0.9 Sverdrups, just the shelf transport. And we see a lot of interannal variability and eddy variability as well. And in 2010, we see this large increase in the transport up to 14 Sverdrup, which I'm going to talk later more about it. And we see also here the eddy contribution to the transport, the seasonal cycle here, and also we see that there seem to have some variability between 2 and 4 years. And how this interannal variability associated with the large scale or gyre properties in the South Atlantic. So here we do some EOF analysis where we kept the two EOF that are mostly correlated with the Brazil current time series, which is in red here in the two. So this is the same time series. In red is the Brazil current estimated with our method. And we see that these two EOFs, one is about 0.3 correlation, 0.3, and the other 0.2. So we see that this one seems to be associated with the northern part of the gyre, with a strengthening or a weakening of the northern part of the gyre. And we see that in 2010 here, it seemed to be what has driven the event in 2010. And the other is more associated with a kind of a dipole, or could be a shift in the location of the gyre. And when we add these two and try to regress and to estimate the Brazil current transport, and then we get this correlation between these two modes, a regression between these two modes and the Brazil current time series, which is in Brazil current is in black, and the regression. So these two modes seem to explain a lot of the variability of the Brazil current at this latitude. And so what happened in 2010? In 2010, we see that a really strong anomaly and of the Brazil current, and we see that associated with the SST anomaly, we see that the SST anomalies in that region close to 22 was up to 3 Celsius above the normal. And we see that from November 2009 to February 2010, we see that seems that these anomalies propagate to the shelf and migrated southward. So the Brazil current may have this associated with these events, may have this impact on advecting this anomaly southward and trapping it inside the gyre. And we see here that this anomaly in 2010 was really above normal in this region. So a little more on this event. So this is the same figure, but here with the wind anomalies, and we see that when we have a strong positive anomaly, we have this anticyclonic anomaly of the winds, which may be related to increase the upwelling in the region too, and the associated this is sea surface height and associated strengthening of the gyre. So here we have one section in 2009, in November 2009, in December 2009, and we see that relate to the DJF climatology in the XBT data for the Brazil current velocity and temperature. So we see here a little upwelling that seasonally occurs in the region of Cabo Frio. We see that there's an increase of upwelling for this event and a really strong Brazil current. So could be associated with that strong anomaly and thermosteric anomaly associated with the strong SST. And we see how along the Brazil current, if we take this and get daily values of sea surface height anomaly and SST, we see that there's a really strong propagation of these anomalies along the boundary. And we see that the Brazil current really spread these anomalies, not seen the SST, but seen pretty well in the sea surface height anomalies, how this Brazil current, the intensified Brazil current, can bring these SST anomalies towards the gyre and trap it in the southern gyre. So this is a quick summary of this first part. So the method was developed to produce the time series of the Brazil current up to 1993. So the modes, it's associated with the sea surface height modes, one associated with the strength of the northern part of the gyre, and the other with seem to be a north-south displacement. And in 2010, we see that the Brazil current was affected to bring these anomalies southward and trap it into the gyre, which may have effects, of course, to the Earth interaction in the region. So to a second part, I'll go quickly on this one. This how the Brazil current will affect the Earth interaction in the region. So for this we use this is a model study in which the way we assess the effect of the Brazil current in the Earth's interaction in the region, we use a couple model simulation, just a control simulation, 250-year control simulation, which one is a coarse resolution, 1 degree resolution, and the other is a 0.1 degree resolution. This is a paper submitted recently to Journal of Climate, where we see what would be the effect of a well-resolved Brazil current in the Earth's interaction. So these are all couple model simulations. I just the main features of that we see. This so this is the low resolution mode, the high resolution, the 0.1, and these are observations from altimetry. We see that in the low resolution, we see that classic feature of the gyre is too zonal, whereas in the high resolution, it seems to improve that considerably. And in terms of eddy kinetic energy, here we see that the high resolution captures a lot of the variability, where the low resolution we can barely see any variability. And compared to the observation, the Brazil current, the high resolution has a much stronger Brazil current than the other one. And so we try to associate this with the event, summer precipitation events in the South Atlantic. So we apply the SVD analysis to this region SST against the high cloud variability, where we see where the convective precipitation is located, and we see that in the observations, the high resolution model and low resolution model, we see pretty much the same pattern here, even though it's generally the second XVD in the high resolution observation, whereas in the low resolution is the first FVD. So this should be more important in the low resolution than in the other. So when you have a strong SST anomaly, you have generally a weak precipitation event in the summer. So what we do now, we compare just composites of this. The warm and cold composites of this region is called the West and South Atlantic region, and analyze that in terms of the Brazil current impacts. So when we have a warm composite here, generally we have in the low resolution, we have this kind of anticyclonic, but really weak here, and a convergence of moisture towards the south of Brazil and South America. Whereas you have this anticyclonic effect here in the high resolution, and lower SST anomalies here, and we see that with the vertical velocity and the Ekman pumping, we see that the Ekman pump is much stronger here in the high resolution than in the low resolution. So it happens. What it does is it cools the water along the shelf, and it makes it associate with this anticyclonic anomaly, which impacts the convective precipitation there, reducing considerably. And this is interesting that the upwelling occurs right on the shelf here. This is the soda in comparison to the high resolution, low resolution. So low resolution doesn't have a represented shelf, and it doesn't produce the upwelling here, whereas the high resolution, it produces one upwelling that is also seen the soda in the soda profile. So it agrees also with the XBT, with this stronger anticyclonic anomaly produces this upwelling, and then this upwelling may have effects in the precipitation in the area. For the cold events, when you have a cold event associated with this region here, we have the opposite effect here. We have the cold anomalies, and it's warmer along when you have a resolved Brazil current here. So the Brazil current, we know that it carries these warm waters from the tropical to the tropical Atlantic to the higher latitudes, and then you see that it increases the precipitation in this area. So it increases the South Atlantic convergence zone because of this effect of the moisture transport in this region here from the high moisture reservoirs here, and along the shelf, when you have a high resolution, we have a strengthening of the precipitation in this area as well along the Brazil current. So in this, and we also see here in the convective precipitation contribution. So the warm Brazil current, when you have a cold event, it increases this the boundary between the cold and the warm waters, and it increases the precipitation. Just to show that, we show a little little section across on 34 south, 34, 36 south in the Brazil current for the high resolution, and the low resolution where we show the SST gradient, the convective precipitation, and the boundary layer. And we see that in the low resolution, we have the gradient are not really strong in the western boundary, and it doesn't cause a lot of precipitation in the region, and the boundary layer is still, the atmospheric boundary layer is small. Whereas when you have a strong gradient, we have a strong precipitation in the region because of the warm Brazil current and the enhanced boundary layer. So because you have this convergence of moisture, and then you have a convection. So just a quick summary. We have these two effects. We use these two models to estimate the effect of Brazil current in the South Atlantic precipitation events, especially in the WSSA, the SST cold and warm events. And we see that really this region in the West and South Atlantic is the one that affects the most the precipitation, at least the South Atlantic convergence zone during the summer. And these events, during the warm event, we have these anticyclonic winds that associated with increased upwelling, and therefore with the cold waters, you reduce the convective precipitation in the region. Whereas during the cold events, you have the strong Brazil current and a stronger boundary between the warm and cold contribution and increased precipitation. So a little bit of future work, and on the first part, so one thing that I've been working on, but I didn't put anything, is associated these anomalies with the wind stress curve anomaly and propagation in the ocean. And the second part, we submitted recently an NSF proposal where we want to investigate more deeply the process in the South Atlantic air-sea interaction, and also the effect of climate change, what the effect of climate change would have on this, because especially in the western boundaries that we know some works say that they are increasing their temperature much more than the rest of the basin. So this may have implications for the South Atlantic precipitation. So yeah, thank you.